In this video, we will solve failure criteria problems. First problem, we have a ductile material, and as you see, the yield strength of the material is not given, but it is known that the yielding occurs for the stress state 1. So for this loading, for this stress state, yielding occurs. In the second stress state, what is asked, the factor of safety for case 2 is asked, and we have to use the Tresca criterion. Well, as you see, this is the stress state where I have to find the yield strength. As you see, sigma x equals to minus 200, sigma y equals to plus 50, tau xy is 0. So since on both of these surfaces the shear stress is 0, well, these two stresses are actually also principal stresses. So these two are the principal stresses in the plane. We note that there is another one, sigma z perpendicular to the surface, which is the third principal stresses. So if you name these principal stresses with proper subscripts, well, the largest one, sigma 1, is 50, while sigma 2 is 0, sigma 3 is minus 200. So for this case, yielding occurs. That means, according to Tresca, sigma 1 minus sigma 3 equals the sigma yield. So let's put the numericals, 50 minus 200 equals to sigma y. Sigma y is 250 megapascal. The yield strength of the materials is 200. Well, you see the same given here, the principles, the Tresca criteria, and the yield strength. We have to check the case 2. Sigma x equals to minus 60. Sigma y equals to plus 90. Tau xy is 30. Okay, you know the stress state for case 2. Well, if you know the stress state, everything is in megapascals. Sorry for missing units. So you can, with the help of these values, you can, for example, draw the Mohr circle, but let us make it simple and let's take the formula for the plane stress condition, you know, sigma x, sigma y, and tau xy, put the values, then you find that the principal stresses in the plane are 96 and minus 66, and as we have already discussed, there is a third one, which is 0. So if you want to name the stresses subscripts, the principles, that is sigma 1, that one is sigma 2, and that one is sigma 3. As you see over here, sigma 1, sigma 2, sigma 3. Next, Tresca. Well, Tresca says sigma 1 minus sigma 3, which is 96 minus 60, that's 162. If you compare it with the yield strength, which we have found for case 1, that is 200, so we will have no yielding, that means no failure. What about the factor of safety? The factor of safety is 250 divided by 162, and that is 1.54. Second problem, we have a rod, radius is given, the length d. D is not the diameter, it's this length. and the force is acting on the surface of this rod at the end. And as you see, the questions are we have to find the stresses in this particular point C, and then draw the Mohr circle, determine principal stresses, use the Tresca criteria, and find the factor of safety. So we can start. Well, this is my rod. Okay, the critical section is this section. It is given to us, and my critical point C lies over here. The acting external force is F, which is 170 kilonewtons. So the question is first to find the internal loadings in the section where my point C lies. Well, in order to do it, I can write down the equilibriums for this free body diagram, or let us do it simpler and save some time because my purpose in this problem is to apply the failure criterion. So in the y direction, that is this direction, you see, well, you reach an equilibrium if you have 170 kilonewton shear force in the blue section. Next, there is no normal force, but we see that this 170 is on the surface and applies a twisting. It applies a torque to the end of the rod, and so a torque in the opposite direction must be here a torque, same value, opposite direction, its value is 170 times this radius. What about the radius? That's 180, 170 kilonewton times 180 millimeters. So in the blue section, we have a torque. Besides, well, we can draw the longitudinal axis of the rod. So when you apply that 170, this rod will be bent, in this direction. So there will be also, for equilibrium, a bending moment over here, and this value is this F times the moment arm, 170 kilonewton times 220 millimeters. So there is no force perpendicular to the section, so no normal forces. So I can write easily that the internal forces acting are a shear, a torque, and the bending. So now we can start to find the stresses. First, we calculate the section properties. I need the area, I need the moment of inertia, polar moment of inertia for torsion calculations, and start with the tau values, shear stresses. Well, there may be shear stresses due to this shear force. This shear force is acting like this. My point C is over here. So the shear stress distribution due to this force V will look like this. 0 on the surfaces and maximum on the neutral axis. So my point C is on the surface, so tau equals to 0. There will be some shear due to torsion. So your torsion in this section will look like this. I will have a tau in this direction. So how do you calculate torque, radius, polar moment of inertia? Put the values. My torque is 3.34 megapascals. What about the normal stresses? Normal stresses are caused by normal forces and bending moments. In our case, there is no normal force. There is only bending, well, in this direction. So in my point C, I will have tension. So this is my bending moment, which looks like this. That's the value. That is the distance of point C from the neutral axis. That one is the moment of inertia, and my sigma is 8.17. So in point C, I have a sigma 817, I have a tau 334. These are my stresses, and my stress state is known is to calculate the principal stresses with these sigma x, sigma y, and tau xy values. As mentioned earlier, we can draw the Mohr circle, or we can use the formula for plane stress condition, write down the numericals, and find that the principal stresses in the plane are 9.36 and 1.19. And we know perpendicular to the plane, there is a third principal stress, 0. And so this is your sigma 1, that one is sigma 2, that one is sigma 3. So you can check, of course, these calculations by simply drawing the Mohr circle. So you know your sigma x was 817, your sigma y was 0, and tau xy was 334. So that was your stress state, 817, and that was 334, and here sigma y is 0. So in order to draw the Mohr circle, you can take this surface, call it A. Well, this point A will have sigma and tau coordinates 817 and 334, and that's your point, as you see. And that one is 0 minus 334. So you see, you can draw the Mohr circle, first calculating principal stresses, putting these two values and drawing the Mohr circle and checking these 2 points, or the other way around. You see, well, in Mohr or principal stress calculations, you can use formulas and you can use the help of the Mohr circle. If you do both, you're 100% sure that your results are correct. I have my sigma 1. That is my sigma 2, that's minus, and sigma 3, sigma 2 is 0. And what about Tresca? Tresca says sigma 1 minus sigma 3, if it exceeds the yield strength, you will have failure. It should be the yield strength divided by a certain safety factor. You can determine, for our case, the factor of safety. Yield divided by sigma 1x minus sigma 3, and over here the factor of safety is very high, 28. Okay, well, these were two problems, how to apply the failure criteria in strength of materials. Thank you for listening.